Hi, this is Adrian, one of the co-founders of the Aurora tracking app Norlys. In today's tutorial video, we're going to focus on our Norlys Aurora tracking model, which is the core of our application. But first, a little bit of history. Ever since I started chasing the Aurora more than a decade ago, I could never find a real good tool that was really giving me a visual representation of the auroral activity in terms of location and intensity. The only things I could find, and I can still find, are, for example, real-time graphs, but those are quite hard to understand and decipher. And a lot of people don't really like the graphs. They prefer a more visual approach. And I'm one of those people, for example. Um, Other things exist. For example, visual models exist, but they're not a representation of the real-time aurora. They're just a forecast. For example, NOAA's version of the ovation model is based on the solar wind, but not on the current translation of this auroral activity. So you're not actually not looking at the aurora, you're looking at a potential representation of the aurora based on the solar wind. So that's not current, it's more of a forecast than a nowcast, if that makes sense. And lastly, you have some visual models that exist that help you locate the oval and also that can integrate a few other tools. But generally speaking, they're not integrating everything like the location, the intensity, how dynamic the aurora is, and the evolution of the aurora. And plus, these tools tend to be very scientific because they come from the scientific community. So they can be hard to use for the layman. And so as a rationale, there was a huge need for a new tool that could really show the tentative placement of the aurora and intensity of the aurora in near real time, and at the same time integrate a user interface that was easy to use and also aesthetically pleasing. Our norlys model is a visual, very important, three-dimensional map of the world that aims to show the probable near real-time activity of the aurora and its location both in the northern hemisphere and the southern hemisphere. We set the model as the app's landing page so that any user could open the app and see at a glance what the aurora activity was doing right now and what it has been doing for the past 2 hours. It's very visual, very didactic, rather accurate, and probably the easiest way to understand what's really going on with the aurora in the world. Something very important to understand about our model is that it's not a forecast. It's a nowcast of the aurora activity. It's not built on a guesstimate of how the solar wind, which by the way powers the aurora to a great extent, may or may not produce some auroral activity, but rather based on the near real-time global observations made by ground-based instruments called magnetometers. These magnetometers sense the variations in the magnetic field created by strong electrical currents of the ionosphere, which are themselves associated, of course, with the geomagnetic activity. Now, one of these ionospheric currents, namely the auroral electrojet current, has been widely demonstrated to be associated with a great part of the auroral activity and the auroral oval in many scientific papers. That's the reason why Hugo and I thought of using the global array of magnetometer data that are available to us and create a back-end ionospheric current map. And this map shows you the strength and direction of these ionospheric currents. So we don't use the map as such, but we just use it for the calculation of our model in the back end. So from there, we can identify the eastward and westward electrojet current, which represents the oval to some great extent, especially on the night side of the Earth. This secondary map already locates the strong currents of the ionosphere, and so by proxy, and thanks to the close relationship between ionospheric current and auroral activity, it can help us draw a tentative map of the auroral activity, which features the potential strength and location of the aurora. Now, our model is far from being the first and only model that uses this technique, and I wouldn't want to sound revolutionary or anything. What makes the model unique, though, is its dynamism, its responsiveness, and its user interface. It's also quite a unique model when it comes to the area of the world that's being covered, and so the number of magnetometer stations that are being used. We've actually gained access to no less than 80 stations around the world, and we actually want to thank all of the big agencies we contacted for providing the data, especially Dr. Magnar Jonsson from the TGO, the Tromsø Geomagnetic Observatory, for helping with the data and the model as well. So thank you so much. All of these stations allow to be rather precise about any local auroral activity that could easily be left out and missed by global averages, like for example the KP index. So in this part, we're going to show what the model actually features and how to use all of these features to your own advantage. Our model shows a 3D globe that you can easily manipulate around with your mouse if you're on a computer, or with your fingers if you're on a mobile device. To move the globe in any direction, tap and hold your pointing device to drag the map around. You can also zoom in on it and zoom out of it by pinching or scrolling in and out on a phone or a trackpad, or using a scrolling device on a mouse. One of the first cool features that you'll see on the model is the sunset sunrise terminator line. The lightest shade of gray on our model represents the sunlit face of the Earth, so the daytime. This sunlit area also shows you the area where it's impossible to see any kind of aurora activity on Earth, even if it's present in the sky, because the sun washes out any kind of auroral activity. The thin band of darker gray shows the area of the Earth where the sun is between 0 degrees and 8 degrees elevation under the horizon. In other words, between sunset and somewhere into nautical twilight. This serves as a sunset locator, and it's a zone where it's a little bit too bright to see any kind of aurora activity just yet, even when it's strong. Finally, the very dark gray shade represents any area where the sun is below 8 degrees under the horizon, and therefore the area where the aurora can be observed on Earth. Please be advised though that you may get a little bit further away from the transition band to see the fainter aurora, as the sky may still be a little bit too bright to see the fainter stuff. Another very neat feature of the model is the integration of a wide variety of webcams, which will allow the users to easily confirm the presence or absence of any aurora activity at that location, provided, of course, that the webcam is on and not under a thick layer of clouds. Now, when you open the model, you're basically zoomed out, so you will see only a limited number of webcams. To mediate this, please zoom in on any specific area of the map, and that will reveal more webcams. If you want to make the content of the webcam just a little bit bigger, because sometimes you're on a computer and the webcam may appear a little bit too tiny, just click or tap on the camera or the name of the city, and that should expand the picture or the camera. What about the zone of study? Well, the zone of study is basically delimited by where magnetometer stations are, plus a little bit of a buffer. You can easily view this area on the map with a light gray dashed line stretching roughly from Alaska to the west, to western Russia to the east, and then that encompasses a little bit of the polar cap and lower geomagnetic latitudes such as mid-Europe, southern Canada, the upper US to the west. Also, your location will be indicated by a blue dot on the map if you allow location services, that is. Now, the model shows the probability of strong aurora with a scale going from dark green to a very white green, respectively from low probability to high probability of strong aurora. Now, why did we use the wording probability of strong aurora and not just auroral activity? Well, it's important to keep in mind that our model is probabilistic and can therefore not guarantee 100% the location and strength of the auroral activity, even if it's rather accurate. That has to do with the fact that ionospheric current activity does not represent 100% truthfully the auroral activity. We want it to remain as scientifically accurate as possible, and that's the reason why we chose the term auroral probability. As a matter of fact, The weaker, fainter aurora is always a little bit harder to determine just based on ionospheric currents. And so that's why the scale only takes into account a certain higher level of aurora activity and may omit the very faint aurora altogether. If you click anywhere within the zone of study, you will see a score of activity appear. This score is from 0 to 10 and indicates how probable it is to see decent aurora activity. Our model is updated automatically every minute. It retrieves all the data and calculates the model in less than a minute most of the time, making it near real time. This allows for the swift detection of the fastest auroral breakouts, for example, a quick substorm expansion, as we'll see a little bit later. By default, our model shows you a nowcast of the auroral activity. Recently, we've implemented a new feature in which our model stores the data of the last 2 hours and makes it available to you for review thanks to an interactive time bar. You can either go back to a specific time by actioning the slider, or you can press the play button to produce a short time lapse of the past activity over the last 2 hours. This new function is extremely helpful because it enables users to check the substorming activity, if there has been any auroral substorms, and or what phase of the substorm the user find themselves in. In other words, it's a valuable tool to anticipate what is likely to happen in the near future, and this is why I need to explain to you how this works a little bit better. The night side auroral oval often has a strange and elusive behavior. It actually rarely dances for hours on end, just as many people think. Instead, it works in a build-up, then release process called auroral substorm. During the build-up process, also known as the growth, the aurora is often faint and will appear with a relatively low score in our model. In real life, you will likely see a stable, quiet, east-west oriented arc, slowly extending towards the equator, just like when you extend a rubber band. When and if conditions are right, this arc should suddenly brighten up, get very dynamic, and shoot back towards the pole. That's what we call the expansion phase. So that's the second phase of the substorm. It's a little bit like when you're releasing a slingshot that you've been extending, and then boom, release it, just like a rubber band. Slingshots back towards the pole. The expansion will manifest itself as a sudden and quick green brightening in our model. The strength of the substorm, though, will be indicated by the score when you click on the brightest green area in the model. How green our model is often represents rather well how bright and dynamic the aurora substorm or the aurora activity is itself. Generally speaking, a score below 2 or 3 out of 10 means that the substorm or the aurora activity is on the less dynamic side and the less bright side. Now, please bear in mind that the aurora can still be beautiful, bright, and a little bit dynamic with a score below 3. Okay? But generally speaking, a score below 3 indicates that the aurora is a little bit less bright and a little bit less dynamic. Anything above 3 out of 10 commonly translates to increasingly more dynamic and bright aurora. So when you get close to 10 in an area, that typically means that you're very, very likely to see a bright and dynamic aurora. Now, just like the previous statement, with a score over 3 out of 10, it's also possible to get a less dynamic and a less bright aurora. So it's not because the score is above 3 out of 10 that you will necessarily see a bright and dynamic aurora. It tends to be the case, but on some occasions, it's simply not the case. Now, a little bit of a tip for you. Keep in mind that it's always best to use our model over the span of several minutes and not only for 1 or 2 minutes. And the reason for that being that we've integrated into our model several components like magnetometer derivative, which will make the aurora bright as a blob, but only for 1 or 2 minutes in our model. And so a sudden brightening, if it's not sustained in the model, doesn't necessarily mean auroral expansion, and so bright and crazy aurora. So what you typically want is the brightening to be constant and persistent over several minutes. That's why we advise you to use the model over several minutes. Now, another tip for you is to use our model alongside other tools in the Norlys app. It's actually the best way to monitor substorm activity, to know in which phase of the substorm you're in, and also to anticipate these substorm expansions. For example, you can use the 2-hour archive to see if there's been any expansion in the past 2 hours. You can also use the high latitude index. If it did peak and if you've seen a substorm expansion in our model in the past 2 hours, you may have to wait some hours to see a new one. If you haven't been able to determine a substorm expansion in the past 2 hours using the tools that we've just talked about, then be patient because there might just be one around the corner. To confirm this and get ready in anticipation for the substorm expansion, please monitor our model regularly as the values and webcams may give you hints that the expansion is near or imminent. Finally, our model is also a very good tool to use to locate the latitude of the aurora relative to you so that you know in what direction to look or to shoot if you have a camera in the field. One thing that you really need to understand is that our model is merely experimental. It's based on theoretical science and scientific observations. However, it's not peer-reviewed as of yet and not associated with any scientific entity. It's simply the fruit of two passionate citizen scientists. I can easily say that our model is relatively robust and reliable and accurate, and we've been testing it in and out of the field for almost 2 years now. However, it's always good to keep in mind that the model is based on a proxy of the auroral activity, and so it can never represent 100% what happens in reality. So there will be discrepancies, there will be errors, there will be misinterpretations. Now, on top of that, instrumentation, data acquisition, and magnetometer distribution are heterogeneous, which leads again to more discrepancies and errors in our model. On that note, there are areas of higher confidence than others, for example, because of the higher concentration of magnetometer stations in some areas, whereas some areas are less dense in stations. And so we had to make the interpolation stronger, and our model is much less confident in these areas. For example, Russia or Canada either don't have a lot of stations or they're not functioning properly. You might have noticed that our model also shows the southern hemisphere oval. It's been pretty well documented in the scientific literature that the northern and southern ovals are what we call conjugate, meaning mirrored. In essence, that relationship enables us to kind of copy paste the northern oval into the southern hemisphere with a few adjustments. However, recent studies have shown that the two ovals are actually a little bit more different than what we once thought. That's the reason why we advise you to take the southern oval version with a little bit of a grain of salt. Keep in mind that the southern oval should still show you the general substorm behavior and timing, but the localization and strength may differ from the northern oval. We've noticed that some of our users, especially the new ones, have gotten surprised or frustrated to see very weak or almost no auroral activity in our models at times. But that's how the aurora works. Most of the time, the aurora is quiet and gets enhanced only on sporadic occasions, especially during substorms. Again, our model is not a forecast like the ovation model, which shows some continuous auroral activity depending on solar wind conditions. Our model is a nowcast of the aurora, so it's normal that it appears weak and empty a lot of the time. Although it's almost impossible for the oval never to contain any auroral activity, there are many times where the auroral activity along the oval is very weak and almost absent. In such cases, magnetometers will not feature many variations, and therefore it's normal that our model will not show much activity. When you don't see anything much in a model, it's important to keep in mind that you may still see some aurora activity in real life. To mediate this, remember to click around on the map to detect weak values that are hard to detect visually, typically values between 0 and 1 out of 10. Then monitor the model continuously over several minutes to spot the appearance of the oval. Lastly, check webcams regularly to verify the evolution of the oval when the model fails to show it. You can find more thorough information on the model by heading to the More menu, then click on About the Model. Thank you so much for watching. It's been Adrian from the Norlys app. Happy aurora chasing.